Alright, this is number 3 from the 2011 AP Physics B exam. This is primarily a modern physics problem. And we've got the interference uh, problem. In this case, it's going to be a single slit interference pattern. We've got two metal strips. We're bringing them together until their edges are separated by a distance d, forming a narrow slit. Now we're going to design an experiment to help determine that slit width. And so first and foremost, let's determine all of the available equipment we need. And really, there isn't a whole heck of a lot. We need a light source, so I'm going to pick the laser pointer. We're going to need something to measure how far away the light source is, meter stick, and to measure the width of the inevitable diffraction pattern that takes place. You can still use the meter stick for that. I think it'd be appropriate to also pick the metric ruler, so long as you very clearly state that you're using that metric ruler differently than the usage of the meter stick. If you can do both tasks with the meter stick, then that's the only thing you need. I also do believe that you need a screen. Now, perhaps we don't need the screen. It's implied that it's already there. I've looked at the answer key for this, and it doesn't indicate that you need to select screen. So perhaps this is just an optional one, but they were looking for these two devices being marked. Next, we need to sketch a diagram of our setup and label the pieces of the equipment that would be used. Please make sure you label it. I can't stress how important that is. It tells you to. You need to do it. And for that, we're going to shine our laser off to the right. It's going to approach that narrow slit. And then on the screen, it's going to create my pattern. So label this one and label this one. That's it. That's the whole setup. Now we need to discuss the experimental procedure that we would use, and then we also need to include a list of quantities to measure. And then for each quantity, we need to identify the equipment we're going to use to make that measurement. Now for this, it's going to be very difficult to tell you exactly what to write down because everyone's experiments can be a little different. For some of the things that you got to make sure you indicate. You need to indicate that you shine the laser through the slit. I know it might be a no-brainer, but you need to say it. You need to indicate that you're going to need to use the meter stick or the ruler. Be very clear which one you're going to use to measure the distance the screen is away from the slit. You also need to indicate that you're going to use the meter stick or the ruler to measure the slit width on the screen for the central maximum. And you should also indicate that you know that there's going to be an interference pattern formed. You're looking for the width of that central maximum, which is basically the distance between the two dark spots. I would also write down what variables you're going to represent each. The distance to the screen you can call L. The width of the slit, the pattern formed, you can call delta X. The distance width of the narrow slit is D. Write that stuff down. Indicate that. D. Explain how you would calculate the slit width by using the measured quantities. To explain this, I want to draw a very crude representation of the pattern that we're going to get. So let's look at the screen, and you're going to get a pretty wide central maximum, and then you're going to get significantly lower intensity and narrower maxima as we get further away. And if you recall the single slit equation, d sine theta equals m lambda. This is for the location of the first minima, not maxima. I'm going to take this and I want to expand what it looks like. Here's my central maxima, which means that edge is the location of the first minima, that edge is the location of the second minima. I'll draw those edges in black actually so we can see that a little easier. The dead center of that bright band is the dead center of the opening. Okay? This is that narrow slit. The slit itself is D. The distance away from that opening is L. When we look at this, if we were to create our little right triangle here, here's my angle theta. Theta is the angle where the first minima takes place. If we solve for where that is from the center line, we know half of that bright central maxima. Or another way of thinking about it is if I measured this distance, like I said I was doing with the meter stick or the ruler, half of this distance is what we need to use in our equation. Now you can use the small angle, I don't know what's going on with my program here, but it's flipping out on me, right? You can use the small angle approximation because you typically can do that with single slit interference pattern, but also because that width of that central band will be significantly larger than the distance you are away. Or you can recognize that tan theta is x over L, and then you can find theta and then plug it back into the d sine theta equation. I'm going to use the small angle approximation. I'm going to say that d, not sine theta, but tan theta, which is really x over L, can equal m lambda. X is the actual width of the central maximum. We need to use half of that. So, I don't care how you state it. If you say the initial x that you created is x central, then the x that we are using here is got to be 1/2 of that. But more or less, it's just really important to directly put that into equation. So let's just get, well, I'm looking at this. What's wrong with me? This is lambda, not L. Let's get d by itself, and I'll come back to that. So d is going to be L m lambda over x. This x is not the x that we measured. It's not this guy here. So let's go ahead and toss numbers or letters in now. Let's say we call this delta x. Then x is delta x over 2. And that's what comes down here. So really, we're looking at 2L. M is 1, so we can ignore that. 2L lambda over delta x is what we need to do. L is a measured value. Lambda is a given value. And delta x is also a measured value. Obviously, you need to explain how you're going to use this stuff. This is the equation. Explain how you explain that L is the measured value distance to the screen. Explain that delta x is the width of the central maxima. The reason the 2 is in there is that we're using half of that. We're dividing by a fraction, so we're multiplying by the reciprocal. Okay? E. Suppose the distance d between the strips is increased. What's it going to do? Everything else is kept the same. Explain what's going to happen and explain your reasoning. Well, I don't know. Let's think about this. The two variation that we can possibly have right now are x and d. They're inversely related, aren't they? X is below the fraction, d is above the fraction. So if d goes up, x must go down. That means two very clear things that you need to indicate. The width of the central maximum will decrease, and the location of your fringes will decrease, because x is really the distance from dark spot to dark spot. So if that goes down, then that means the fringe spots, those bright spots, will get closer to each other. Indicate what will happen and why you know it, and it's because it's an inverse relationship. Okay, that's it for this problem. Thank you.